At the beginning anyways, we don't need it.
Steven?
Yes.
On the Moodle, is there a last year video?
Last year what?
About the uncertainty.
I thought there was. Maybe there's not.
I can't find
Anyway, this video's on my YouTube channel.
I'm a subscriber.
You subscribe?
Yeah.
Unfortunately, I have two YouTube channels.
Ah.
One that has like 1,000 videos and another which has like 20 videos. So just make sure you're subscribed to the one with the 1,000 videos and not the one with 20. Because that's probably like the one with me on holidays or something. That's what you remember. You want the one with the math classes in it. Alright, so in this one, we're just looking at a bit of vocabulary, really, and concepts for your lab writing. Have you finished the draft?
Yes.
Do you want me to look at it?
Yes.
Have you got it with you?
Yes.
Okay, well, cough it up. What about you? Draft?
The graph.
Minus the graph, okay.
So I'll just show the graph in the group one.
Right. Oh yeah. Oh yeah. Of course you need the names in this diagram.
Yes.
How many videos?
It's only 2 videos, not thousands.
No, this isn't it, because you can see from the time, the last one was 11 months ago.
Yeah.
That's the wrong channel. Maybe I should just delete that channel, I don't know. I'll put a link, and this needs the units in it. I'll put the link on Moodle. Okay, KJ, you are looking good to go. You finish this up, put it in the final draft version, and yeah, I think we are good with this. So good job. Congratulations to you. Yeah. Okay, you got your notebooks now. Let's have a look at this. Yes, well done on earning 2%. The hardest 2% you ever had to earn. Although the value in it is that it will help you do the typed ones. You have a better idea of what you need to do in the typed ones. With the tables, you know, the graphs, the equipment diagram. Alright. Have you got this? Come on. No, Yemi and Karar. Is the chemistry due this? I was talking to Lorraine yesterday.
Yeah.
Rather interesting. I was asking her, I was talking to her about my physics students, and I was saying, oh yeah, they don't have their physics lab done. You know, like blah blah blah, not enough time, blah blah blah. And I said, is their chemistry lab due? And she said, yes. They haven't done it. I'm like, oh, I see. They haven't done their physics and their chemistry. So they're doing what with their time? Not their work, that's for sure.
Yeah. We have
And I think carefully, because what you say could make the situation much worse. Yes?
Yesterday,
Yes?
actually, we
Yes?
didn't know, like most of us,
Yes?
that we have to print it.
Yeah, exactly.
So you're pleading stupidity.
But we have done it, like we emailed her yesterday.
Okay, alright, whatever. Okay, we got this. Come on, Fahad, I'm waiting for you to write the title down.
Yeah, it's okay. Oh.
Got it?
Yeah.
Yeah. What's wrong?
I was looking at it, I was writing this.
Okay. Right. Now look, you don't need to write everything down, because there is a lot to write down. Yeah, actually it is. I'll just turn this off, okay?
It was not?
Yeah, because Grace, it's cold. Grace and Amanda. Right. You don't need to write everything down, but the key points you need. And I got all this information from this website. So, I mentioned this before last week. In order to reach a conclusion from your data, the uncertainty must be given. For a result to have any meaning, you can't just have the result. You must have a measure of how accurate or precise the result is. So if I tell you that the experiment says G is equal to 10, it's no use without some kind of knowledge on how accurate that is. Okay, so this is an important part of the experiment. In fact, well, for any result there should be two parts. The value, of course, and number two, how uncertain that value is. So when you give a result, you should always think, what are the two parts? What is the value of it, obviously, but how uncertain are you about the value? So I hope you can all appreciate the importance of having an uncertainty value with your result. Okay? It's something that you must have, it's not optional. Yeah? Right, so what do I mean? Some terms. Now if you know these terms, if you got them from chemistry, if my definitions are the same, then you don't need to write it down. But if there's a little bit of a difference, or if it's a new term, you need to note it. So true value. What would we mean by true value?
Actual results.
Yeah, but give me an example.
Literature value.
Huh?
Literature value.
The what value?
Literature value.
Oh, yeah, okay. Yeah, something like this. So the true value cannot be absolutely determined. You can never really know what the true value is. In practice, an accepted reference value is used, what you're calling the literature value. The accepted reference value is usually established by doing an experiment many, many times in some repeatable way. This value is not the reference value that's found published in a reference book. Such reference, I wonder if that should say, yeah, such reference values are not the right answers. They are measurements that have errors associated with them as well, and may not be totally representative. So let's just go through that again. It's not quite the same. What would you call this in chemistry? We call it literature value.
Yeah.
Do you have true value in chemistry?
Yeah, we have concentration values. It's like 0.1. Don't you?
The true value and the literature value are not technically the same thing. Just be careful. The true value, the literature value is like almost trying to be as close to the true value as possible. But the true value is something that you can never really know. Like you imagine it, the true value is out there, and your experiment is trying to get to the true value, but you can never really know if you're at the true value. You know?
Oh, okay.
So the literature value, we think of this as being the true value, but really it's just an extremely accurate result, but it's still not the true value. Even the literature value has uncertainty in it. So if you look up the value of G, it's 9.81, but this isn't the true value. Even the literature value will have 9.81 plus or minus 0.0000001 or something. Okay? So in your head, think of the literature value as an extremely accurate result, but it's still not the true value. Okay? So how would we summarize true value? It's almost like the goal that you can never be sure if you're there. Do you get what I'm saying?
Yeah, I'll get it.
Yeah. Write some sentence down to help you remember this definition about true value. You certainly don't need to write all of this down, but write something down. Yeah?
This is something like the actual value of something.
Yeah, let's try and use a different word. Almost like the...
Because of
Yeah.
different interactions, you cannot get it.
Yeah, I'd say the true value is a value you're always trying to reach, and you're never sure if you're there.
But you can reach, like if you create a situation like perfect,
Yep, you just create a perfect situation for. No, you can't. You can't.
you can. Like for example,
Yeah.
for like on zero gravity we perform any law,
Hmm.
first law.
Hmm.
Yeah, then we can, at least, no, that's it.
It's not possible. You can just make it smaller, but you can't make it zero. And in fact, later in the course, we'll actually prove it's impossible, even in a perfect situation,
Even in space.
even in a perfect space situation. Yeah. There's always some uncertainty of a minimum value.
And how is it like a proof is solved?
Well, this is it. You can't. Laws, physics laws aren't like maths laws. They don't really have proofs. All that they have is evidence that makes us think that they are true. But it could turn out one day that the law we were using is not completely accurate. And that actually happens frequently in physics.
Something you might know.
So somebody can say Newton was wrong.
In Big Bang
No,
Theory there was.
just that you could have another formula which is nearly the same as Newton, but is more accurate in certain situations. So not that Newton was wrong, because his formula obviously works in lots of situations, but it might turn out that there's a more accurate formula. This
Like,
is not unusual, this is actually normal.
like in the Big Bang Theory, the physicists try to prove on theory like thing.
Yeah, but the problem is with use of English. So like you can prove a theory or a result mathematically, but trying to say that this formula represents the real world, that's not something you can prove. It's only something you can believe to be accurate practically. So for example, I cannot prove F equals ma for the universe. I can only do experiments that show that it's probably true, because when I did this experiment 100 times, it was always true. So maths formulas and physics formulas, when we say proof, it has a different meaning. In maths you can prove a formula is always true. In physics you're only proving the formula is true, or we think that it's true. But like I said, it might turn out one day that Newton's formula is not 100% accurate. And in fact, we already know it's not 100% accurate, because Einstein's formula is more accurate than Newton's formula.
What's that?
This is something that you'll only see at university if you study advanced maths. If you're doing engineering, you will never see it. Sorry to tell you this. Alright, have we got something for true value?
Yes, I don't want to see it.
That's fine. If you're happy with this, that's fine. The only time, Fahad, you will see this formula if you're doing engineering is if you're doing anything with GPS. Because for GPS you need to be extremely accurate, more accurate than what Newton's F equal ma formula will allow. Okay. GPS is an extremely accurate branch of physics. Okay.
You might see.
I want to see, like have some music and see whether.
Yeah. Alright, next slide. Yes?
Don't worry, after university I'll hack your house.
Oh.
You see my face on your TV.
Right.
Hello, Stevie.
You're watching too much Flash now.
Or maybe Steven has a lab in the basement.
That's right, actually. Maybe I have some kind of bat lab in the basement.
Yeah.
or arrow cave.
And
Possible.
he keeps, like eyes on his students.
That's it. Maybe I'm watching you as you leave. Like, he's not doing his physics homework. Right.
That's why he don't use iPhone, like some smartphone that nobody follow or something, check.
Yeah, that's the real reason. Yeah. Right. Accuracy. Accuracy, you would know this from chemistry as well.
Yeah.
It's how close your measure value is to the true value. So, what would be the most accurate machine you used in the chemistry experiments?
For accuracy.
Hmm.
Maybe 2 moles of volume, that's effect.
bits.
you feel was the most accurate
Yeah.
thing? Yeah.
Because it has the low tab 0.03.
Okay. Right. Now, of course, you know what error is. Error is the difference between a measurement and the true value, and this is what you want to make small. But there are two types of errors, as far as we're concerned. The first one, oh yeah, an error does not include mistakes. So if you, I don't know, turn the machine upside down, that's not an error, that's a mistake. If you measure the meter stick from 100 centimeters instead of 0 centimeters, that's not an error, that's a mistake. So if you do something stupid like that, that should be excluded from your data. Mistakes are excluded. And explained why you excluded it. You said, oh, Tekken distracted me and the meter stick was upside down, so I've excluded this value. Error is what causes the difference between something which is measured each time, even if you do the same thing each time. It's not, you probably know this, it's not possible to cancel error completely, okay? You can control it, but you can't remove it. And just to say, calculating the error can be something difficult to do, but important. So anyways, you have an idea of error, but more importantly, the two types of error. So the first one I already kind of mentioned. Systematic error. Oh, it's great if you can get this vocabulary into your report as well. Systematic error is an error which causes the same difference each time, or in a predictable way. The cause may be known or unknown. So look, basically, imagine, I'll give you an example. Look up, imagine you have a weighing scales, and the weighing scales is not calibrated correctly. So when you put 50 grams on it, it says 51. When you put a kilogram on it, it says 1001. When you put 20 kilograms on it, it says 20,001 gram. You know, each time it's adding 1 gram. So this is an example of a systematic error. It's the same error being added each time. Sometimes you can reduce this. How would you reduce it with the weighing scales? By calibrating it. So you put 1 kilogram on the scale and you adjust it until it says 1 kilogram. Oh, a lot of scales can be calibrated, yeah. So systematic error is sometimes the cause is known. Sometimes the cause is not known. And of course, if you don't know what's causing the systematic error, then there's not really much you can do about it.
But we mentioned it, you know, because if our result is not maybe near accurate.
Yeah, sometimes you can see if there's a systematic error if you notice that each time your result is slightly more than you thought, you know. Like maybe the watch is fast or slow or something like this.
This thing was happening here when we were calculating this U and V. Sometimes it just went big, sometimes I know.
That wouldn't be a systematic error. Systematic error would be the same mistake each time. An example with the U and the V of a systematic error is if you measure the wrong distance between the two light gates, then your A will be wrong each time, but it'll be wrong for the same reason each time, that the S is wrong in the formula. So systematic meaning each time. Okay, so we're clear on systematic error.
Which causes the same difference again and again?
Yeah. Okay. Then you have random error. Do you know this one, random error?
Yeah.
So like just to be clear, when we talk about error, we're thinking error has two parts. A systematic error, the total error is the systematic error plus the random error.
There is no human error?
Well, again, I'm counting human error as part of systematic.
Yeah.
Human error could just mean that you didn't calibrate the weighing scales. Something like this.
The word count, you can mention it.
Yes. But please don't confuse human error and human mistake. So human mistake is, you thought you put a 50-gram weight on it, but you really put a 60. That's not an error, that's a mistake.
Saying 50 instead of 51.
That is a mistake, not an error.
No, it's like an error, like parallax error. Maybe you're looking at.
No. If it says, oh, okay, sorry. I was picturing a digital display. Yeah. So, yeah, the digital display said 50 and you wrote down 51. That's a mistake. We agree on that.
Yeah.
But reading a scale and reading it wrong the same way because of a parallax error, yeah, that one is a systematic error, not a mistake. Then that one could be fixed by replacing the measurement device with something that's digital, maybe.
But we know we have the Snell's law like this.
Yeah, so that reading would be an error, not a mistake.
Yeah.
Yes, yeah. Okay, so random error. What's random error? Do we know?
That happen like we don't know. That causes our child.
Yeah, so random error. Firstly, you don't know what the cause is.
Yeah.
What else?
It could be gravity, air temperature.
And it's an error.
Yes.
Yeah.
Like it could be like temperature error, room temperature error.
Yeah, random error is something which you don't know.
We can't do about it.
And its difference is unpredictable. It's not possible to correct for this. A systematic error you could fix, a random error you can't. So what would be examples of random errors? Well, the light moving in the Snell's law experiment.
In the both meters there was like up and down too much.
Mm-hmm. Yeah. Yes. Are there any terms which you know from chemistry which I've not used from the lab?
In physics?
Yeah, like I'm saying, is there a word in chemistry you have that I haven't used in physics?
Relative error.
Yeah.
Relative error.
Yeah.
Okay. Which is like the percentage error, isn't it? Yeah. Yeah.
After that we done the error calculations. Then we do the literature value minus error.
Yeah.
And relative error.
So that's the relative error. Yeah. Trueness and bias is the closeness of agreement between the average value obtained from a large series of test results and an accepted true. The terminology is very similar to that used in accuracy, but trueness applies to the average value of a large number of measurements. Bias is the difference between the average value of the large series of measurements and the accepted true. So this is a bit like your relative error. It's the difference between your result from doing the experiment many times and the accepted literature value. So for example, you did the pendulum experiment 10 times and you got a G. You can compare that with the literature value of 9.81 and the difference is called the bias. You can make it a percentage if you like, and this is called the relative error, isn't it? That's what the relative error is the percentage difference. So I don't personally mind if you do it as a bias or a percentage. So you could say the true value is 9.81 and I got 9.8, so the difference is 0.01 as a bias. Or you can do it as a percentage and then it's a relative error. Both are fine. The reason for the bias is because of the systematic error and the random error. But anyways, this is like relative error. Yeah? Right. Now, precision. What's that? Not quite the same as accuracy.
It's like to be more precise, to be more accurate.
Yes. Precision is the closeness between independent measurements under the same condition. So, in other words, imagine you measured somebody's height and then you measured their height again, you should get the same result, right? Right?
Yeah.
So precision is, you say something is more precise,
Yeah.
the more similar the two measurements of the same thing are. So for example, an example of something that wasn't so precise is the voltmeter. So although the battery wasn't changing and the resistance wasn't changing, you notice that the voltage was jumping up and down.
Yeah.
So this is not very precise because the same thing you're measuring did not have the same value. So precision is more to do with the machine. How well the machine can measure the same thing the same way, the same time. You know, so the meter stick is precise because the thing isn't moving.
Yeah.
The Snell's law one and the voltmeter and the ammeter, not so precise. The light gates,
No.
yeah, they weren't too bad.
No. Like, out of 20 maybe, no, 10?
No, but the problem with the light gates is you're not, every time you do it, you're not repeating it exactly the same way because you're putting the trolley at a different starting position.
No.
Yeah, no, Fahad. You are. Because did you mark a line on the table?
Yeah.
You did.
Yeah.
You really did.
Yeah.
But I didn't see that.
No, you can ask, we put the marker line at the look at the top of the tire.
Yes?
The tire is exactly after the line.
Okay, and each time you did the two, remember you did each one twice, how different were the two U's and V's?
Like sometimes it was a bit different, like point zero something different,
Yes.
like 0.81 or 0.80.
Yeah, okay.
But sometimes if we did 0.80, the next one could be more than 1.
Okay, so the precision could be as different as 0.20 for what seems like the same thing.
But we don't count it, we just do it again.
Oh, so you did it 3 times?
Yeah, sometimes more.
Oh, I see, okay.
So we didn't want to add, too much confusion in our results.
Don't mention that in your lab report. Yeah. This isn't, you're not supposed to do it that way. You're supposed to record every measurement. Yeah. Anyway, precision. So, I don't need the whole thing here. Yeah, I know. We have relative uncertainty and relative, anyway, we know what precision is from our little conversation. The pipettes that you use in chemistry, that was precise.
Yeah, but it looks funny.
And it looks funny, but it was precise. Right. Now the big thing that really I'm trying to build up to, the important thing here, precision and accuracy, these are good things to mention in your report. So you could say how precise the light gate was. You could say how much the causes for the error. You could say the bias between your value and the literature value. You can calculate the relative error. But the most difficult thing to maybe calculate is the uncertainty. And the uncertainty is how different your value is. It's putting a boundary on your reported value. So you have a responsibility to say, when you give a value, what you feel the potential error, the potential mistake you could have made is. Okay, this is the uncertainty. It is an estimate of how big your total error is. Now, it could be random, it could be systematic, but the uncertainty is trying to quantify, try to measure how big of an error is in your result. And to do this, you need to know how much uncertainty there was in your measurements. This is why I made you write the uncertainty of each measurement in your table. The uncertainty for the I, the or, the T, the length, the V, the I, everything. Okay. So what we're going to have a look at now is how we can calculate uncertainties. So I'll do it in Excel just to make the calculations easy for me, but you know, you do this in pen and paper. So just to give you some something to think about. So imagine I was measuring some distance here, I'll call it x, and then I was measuring here some distance here, y, and let's say this measures as 1 meter and this measures as 1 meter, but I think there could be a half a centimeter error here. There could be an uncertainty of x to be half a centimeter, the uncertainty of y to be half a centimeter. So when I add x and y together, how uncertain am I about the answer? How does the uncertainty combine in this situation?
The formula?
No, like if I said x is 1 meter long, y is 1 meter long, together they're 2 meters long.
2 meter plus minus 1
Yeah, plus minus 1.
centimeter.
Yeah, plus minus 1 centimeter.
Plus or minus 1.
Yeah. Yeah. So this here is 2 meters plus or minus 1 centimeter. So in other words, the uncertainty of x plus y is equal to the uncertainty of x plus the uncertainty of y. And that makes sense, doesn't it? So this is how certainty adds. Yes? What's wrong?
I just remember the thing that happened in simplicity.
There was a problem?
Yeah, she got stuck like this, you know, when the plus minus thing, she was like, what?
Let's have a look at the minus case then. Right. So suppose I measure x to be 1 meter, and again the uncertainty is half a centimeter. And suppose I measure y to be 0.9 of a meter, and again the certainty is half a centimeter. And I would like to know, let's call this one x and this one y, and I want to know how big this difference is. So I calculate my x minus y, what will I get? 0.1 meters, true, yes, which is 10 centimeters. But what's the uncertainty of x minus y?
0.1 minus half centimeter.
Just give me the number.
Okay.
What is the uncertainty?
Plus or minus
0.1.
Plus or minus what?
0.1
1
minus.
centimeter.
No.
Which, no, what is it?
Half centimeter.
1 centimeter. Yeah, so again, the uncertainty still adds, even in the minus case. Now, if you want to know the reason why, think about it like this. If I'm measuring this as 1 meter, potentially I could be wrong as far as, it could be as little as 0.995, right? Or it could be as big as 1.005 meters. Agreed? That's what uncertainty means, right? If I measure the 0.9 meter, how small could it actually be? It could be as small as 0.895, but it could be as big as 0.905. Again, because the uncertainty is half a centimeter. Now imagine the worst possible situation. The worst possible situation would be I measured this one too big and this one too small, and the difference is actually, what's the difference here? That is 11 centimeters, is it? Yeah. 11 centimeters. Or the alternative is I made my difference too small. I measured this as only 0.995, and the other one I measured as big as 0.905. The difference here is 9 centimeters. So my 10 centimeters could have been as small as 9 centimeters or as big as 11 centimeters. In other words, the answer is 10 centimeters plus or minus 1 centimeter. So again, the uncertainty still adds, even when you're doing a subtraction on the measurements. Okay? So far we have two rules for uncertainty. One rule really. The uncertainty of x plus or minus y is the uncertainty of x plus the uncertainty of y. Okay, I want to give you a minute to think about this one.
You are equalating. You put equal sign between them.
Correct. Which is correct. What's the problem?
If you add a minus, then there will be equal to the uncertainty.
Wait, what? What are you asking me? What are you asking me? What are you asking me? I said if you add or subtract
no, that I understand.
this you understand?
Yeah, and the rule I understand, but why put equal sign between them?
Because I'm saying,
It's equal.
yeah, I'm saying to calculate this, you need to calculate this. That they are equal. That's why I put the equal sign there. What am I missing? What are you missing? I don't understand what's going on. What's the problem?
If you plus x and y, the difference.
This is the uncertainty of x minus y.
Oh, okay.
That's why the brackets are here. I'm saying the uncertainty of x plus or minus y is the uncertainty of x plus the uncertainty of y. It's not possible to know this. Only by calculating this can you know it.
Okay.
Right. Try this for me. Here is 1 meter. Here is 1 meter. And you measure the area. What's the area here? Well, of course, that's 1 meter squared. This is the x, this is the y. And let's say, again, the uncertainty for the x is half a centimeter. And the uncertainty for the y, let's say, is half a centimeter. So I want to give you a minute to think about this and tell me what the uncertainty in the area is. So the area is x multiply y. Tell me what the uncertainty is here. So while you're trying to figure that out, just
Don't think
what? It's just a square. What do you need?
Yeah, you got it.
Okay.
1 meter plus or minus 0.007.
Hold on there, dude. Hmm.
What do you got?
Right. What did you get here?
1 plus minus 7.071 into 10 minus 6
Sorry, I don't understand. Why divide?
1
time.
1 meter plus or minus 0.00.
Now it should be 1 meter squared at least.
Oh, yeah.
Sorry, squared.
Yeah.
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 one sec, sorry folks. What did I say it was? 0.005, wasn't it?
No, 7.
No.
You can say like
Alright.
1, 2, yeah, 0.007.
Right, that's better. Right, so what did you get for the uncertainty here? Sorry, uncertainty for the area is
7.07
7
times 10 minus 3.
times 10 to the minus 3.
Yeah, 0.07.
0.07.
0, double
0.007
0.
meters squared. What did you get? Now how did you get that?
Formula.
What did you do? You added these together?
No.
Square them.
Square them.
Added them, then square root of them.
Not bad. Not bad at all. Let's have a calculation. What is the potentially smallest area you could have here? The worst case. It could be as small as 1 minus 0.005 for the x and 1 minus 0.005 for the y. So that's 1 minus 0.005. So potentially the area could be as small as 0.990025 meters squared. However, maybe we've made two mistakes in the like maybe potentially the x could have been as big as 1 plus 0.005. So if you change these to pluses, your area could be actually as big as 1.010025 meters squared. This is with pluses. So you could put these answers together and say the area is 1 meter squared plus or minus 0.02 meters squared. So your answers were too small. The uncertainty was a lot bigger than you thought. Because in the worst case, if this was a little bit smaller than you thought and this was a little bit smaller than you thought, the area is only this. In the other case, if the x was a little bit bigger and the y was a little bit bigger, the area could be as big as this. Therefore, the area would be 1 plus or minus, and this number here, actually sorry, I think I might need to have a 1 there. I forgot to divide by 2. Just forget about the extra pieces here for the moment. You can see that the area could be from 0.99 to 1.01. So that is, stick a 1 here. So the uncertainty is 1 centimeter, 0.01. Now your answers were much smaller than this.
Yeah, I got it for one, but because we can just with this.
You know, if we bring it to two decimal places, it'd be 0.01, 0.01.
Oh really? Went 2 decimal places? Cool, alright. Now what about if you had a formula like this? You had, not area, but maybe it was something like, well I'll call it A, but no, we'll call it Z, whatever. It's square root x y cubed over z. Now how does the uncertainty combine here? Oh, yeah. So there is a way to combine certainty for formulas like this. The first step is you write everything as a power. So this is x power a, y power b, z power c. And for your formulas in physics this is possible. You know, like 2 pi root L over G, and so on.
The square root is on y too?
No. Well, it doesn't matter. But you can write everything as a power. So if you want to calculate the uncertainty for z,
what's a?
powers.
Like 1, 2, 3?
No. Well, in this case, it would be a half. Dude, what's wrong? What's wrong? I'm right. You know this. Z would be what? What would C be here?
C.
I'm going to give you 5 seconds to tell me what C is, and somebody's going to die.
Minus 1.
The B?
I'm not sure what you have to
3.
Fahad,
3.
what's wrong? I'm writing this in this form.
3.
The B is 3, and the A is a half.
Half.
3 minus 1.
Oh,
Come on, wake up, Fahad. Wake up, wake up, wake up, wake up. So the uncertainty for the Z, don't do that. The uncertainty for the Z, the way you can calculate it is from the formula. Uncertainty for Z divided by the average value for Z is equal to square root A times the uncertainty for X over the average value for X squared.
A is the power.
Yeah. B, uncertainty for Y over average value of Y
We have this.
squared. Now, but it's a tiny bit different.
Yeah, because there's Z here too.
Yeah, but I mean, it doesn't make it much different.
Uncertainty of Z over.
Average. Oh, sorry. What the heck? Oh, wait. No, that's stupid letters. I'm not calling this Z. I'm going to call it something totally different, like zeta. Because I already used Z on the right.
Yeah.
Zeta.
Okay.
So, for example, with the area equals X multiplied Y. What's the powers here? Power 1 and power 1. So what's the uncertainty for the area? It's square root 1 uncertainty for X over... Now what's the average value of X? What did you measure X as? 1. Now did you include that in your formula you used? Well, I know you don't need to here because it's 1, but did you know that you need this here?
We just lost the
No, please just give me a yes or no. Did you know you need to put that here in the formula? No. Power 1, uncertainty for Y, divided by the average value of Y. So here it is square root 0.005 squared over 1 plus 0.005 squared over 1 squared. That's the uncertainty for A. Oh, and what was the value of average value of A that you measured? It was 1 meter squared. So the uncertainty for A is 1 meter squared over, or square root 0.005 squared over 1 squared plus 0.05 squared over 1 squared. Square root 0.005 squared. Now, the value that you got, that's what I got here. But I don't think you guys were putting in the average values for the X, the Y, and the area. No. So if my square was 2 meters, and this was 4, your answer would still be the same, wouldn't it? No, just, the only thing you put in, look at me. The only thing you put into your formula was uncertainty for X and Y.
Yes.
Yes? What are you doing? No. This is recording. I'm putting it up.
It's hard to find, like
I'm going to put a link to my YouTube channel. You can subscribe and get notified. Your formula, if you put this question in with the 2, the 2, and the 4, is the uncertainty for X the same? No, it is, because it's the same.
Oh, if you say.
Yeah, let's say it's the same, half a centimeter. Okay. Is your uncertainty for X the same? Yes. For Y? Yes. Is the uncertainty for area the same? In your formula, you'll get the same answer as previously, because it's square root the 2 uncertainty squared. Yeah? But it should be bigger, because you're dealing with a bigger square, with a bigger area. So, your formula that you have only works if the X, the Y, and the area, they're all 1 unit. Yes, what's wrong?
In the scale, if it's not even, we are not measuring one something,
Yeah.
even we are measuring like big 24, 30.
Yeah.
We still in the chemistry we count as error the same thing, same.
You don't factor in.
So it's increasing or decreasing, no.
No, but I mean, in chemistry, for example, if you did square root volume 1 squared plus volume 2 squared, the uncertainty would be really small, right? Like whatever, half a milliliter. You don't factor in how much volume 1 or volume 2 are on average. You just
No, we did this before.
no, I just need yeses or nos.
Yes.
So, is this included in the formula or not when you do it?
Yes.
Oh, you do include this.
Yeah.
So why didn't you?
We had two different formulas.
You do have a formula that has this one in it.
Yeah.
Okay, I'd like to see it. I'd like to see it. Right, we better finish there.